We got to verify our flight simulation, so we're dropping tumbling bricks from high altitude over volcanoes. We're using existing 6 DOF check cases to verify our flight simulation. We'll first review the NASA effort that led to the existence of these check cases in about 2015. We will look at the first 3 check cases. Number 1 is a dragless sphere. 2, a tumbling brick with no aerodynamic force. And 3, a tumbling brick with aerodynamic damping. As part of the 3rd check case, we'll review a basic moment buildup, including aerodynamic damping terms. We'll also look at visualization of our simulation results with a program called FlightGear. And finally, we'll briefly run down the bugs and issues that we uncovered in exercising our sim with these verification check cases. NASA created a set of 6 degree of freedom flight simulation check cases. All of the data in this study, including the vehicle models, is openly available for download. I'll put a link in the description below. There's a 2-volume technical report that details each verification case. The 2nd volume of the report is a 600-page appendix. It details the vehicle models, geodesy models, coordinate systems, gravitation and atmosphere models, the 7 different flight simulations compared in this study, and all of the check cases. A check case was valid when the simulations agreed, and the reasons for any differences were investigated, in some cases leading to fixing of bugs or new perspectives. We want to verify that our simulation agrees with the first 3 atmospheric check cases involving a sphere and a tumbling brick. So we use these reports and the data available on this website to begin systematic verification of our Python flight simulation. In atmospheric case 1, a 6-inch diameter sphere is dropped from 30,000 feet with the x-axis pointed down. The sphere was initially still with 0 velocity and angular rates. The standard atmosphere 76 model is used. The forces involved are inertia and gravity. This case will check gravitational and atmospheric models and the U velocity state equation. The simulation time is 30 seconds. We've essentially looked at this case before, but this time we're comparing our data to the NASA check case number 1. Now, let's run the code. Here we are in the main program driver of our simulation. We've selected the NASA sphere model. For 30 seconds, we'll simulate. Our initial state vector, note, the U velocity component is small to avoid divide by 0 in the angle of sideslip calculation. X-axis is pointed down, initially at 30,000 feet altitude. I've made some updates to the driver that allows us to save data and save plots. Let's run this. We drop the sphere directly above the NED coordinate system located at an arbitrary place on Earth. Now, this is a flat Earth simulation, and as such, no rotational model of the Earth is used. So, north and east positions remain 0 throughout the 30-second fall. It follows that no velocity component exists in the horizontal plane, comprised of the U and V components that are resolved in NED. All of the action is in the vertical plane. To compare our data, we look in a folder called Case Studies. Inside is a single folder now called Verification, and in that are 3 scripts. Look at Case 1 Verification. We have some upfront description of the NASA output data, the Python sim output data. We specify where we want to save a plot that compares the results, and here is where we import the NASA data and our data. NASA's data is as a CSV file. Our data is as a NumPy array. That data is imported and figures are created to compare the results. To run this script, we call it from its directory. And we find that our results are visually indistinguishable from the data of the 6 other simulations. Based on this result, we check off case 1 as being verified for our Python sim. We can also visualize our sphere falling over the Earth by importing our simulation results into FlightGear using the Python FlightGear package. We won't go into the details here, but for a basic introduction, check out the tutorial by VD Engineering in the description below. Pretty cool. The next atmospheric test case is a tumbling brick without aerodynamic forces. Again, it's dropped from 30,000 feet for 30 seconds. There are non-zero angular rates of 10, 20, and 30 degrees per second in the roll pitch and yaw rate states. The initial velocity and attitude are 0. This verification case will test the angular dynamics and the Euler kinematics. Back in our main program script, we changed the vehicle model to Atmos 2 brick, 30 seconds of a simulation. Update the initial angular rates. Set all Euler angles initially to 0, 30,000 feet, and we're all set. As with the previous sphere, no forces act on the brick to move it laterally, so the tumbling brick falls vertically, constantly accelerating under gravity. And since it's tumbling, the Euler kinematics are active. Note, there's nothing to arrest this tumbling. We observe this from the oscillation in the Euler angles. Let's compare our results. We're now on case 2 verification. Five simulations in the NASA study had data sets for comparison. First, note the U velocity in NED is 0 for the check cases and increases to just over 1 e to the minus 8th for our sim. While this is effectively 0, the reason is the small initial U velocity component that we applied to avoid singularity in the initial angle of sideslip computation. Also note the difference of 0 eastward velocity in our sim versus the 5 check cases that all show monotonic increase to 2 feet per second. What would cause this? The reason is that the check cases involve an oblate rotating Earth with the brick initialized at the equator prime meridian intersection. Hence, the brick moves eastward as the Earth rotates below it. Of course, this does not occur under the flat Earth approximation, so our simulation shows 0 velocity. Those discrepancies aside, the Python simulation results overlay on the body resolved angular rates and the downward velocity. The Euler angles also match very closely with the check cases. Simulation 2 in green shows a minor discrepancy in roll and pitch angle. Nevertheless, based on the agreement between the check cases and our sim, we confirm this case as successfully verified. The third check case is the same as the previous, but aerodynamic damping is now included. This will tend to arrest the angular motion of the brick. Recall our rotational equations reviewed in section 1.2. This is the first time we're working with aerodynamic moments in these rotational equations. They're named L, M, and N for roll, pitch, and yaw. Let's discuss the formulas we will use to quantify the aerodynamic damping in these moments. We'll start with the roll moment L. The roll moment is the coefficient of roll, CL, times dynamic pressure, times reference area, times reference wingspan, where dynamic pressure is 1/2 air density times airspeed squared. And the reference area is reference wingspan times reference wing chord. That is, we have dimensional roll moment L as the coefficient of roll moment times a reference force, that is dynamic pressure times a reference area, times a moment arm, or roll moment coefficient times a reference moment, where these reference forces and moments characterize the energy in the airflow that hits the body. It follows that the roll moment coefficient is the actual moment on the body, L, divided by the reference moment. And similarly, for the other moments, we obtain 3 basic moment equations. Various aerodynamic effects are all captured in the CL, CM, and CN coefficients in a so-called aerodynamic buildup. Here, our buildup is limited to damping of angular momentum through 2 terms, damping due to roll rate and damping due to yaw rate. Let's briefly explain one of these. The roll damping coefficient is the partial derivative of the roll moment coefficient with respect to the roll rate. As the wing travels up or down due to rolling, the angle of attack of the wing decreases or increases respectively. This causes a change in force on the wing that opposes the rolling motion. The greater this derivative, the greater the roll damping. The roll damping is proportional to roll rate. As the body rolls faster, there's a greater change in angle of attack per unit time, and hence a greater moment due to roll damping. The reference wingspan is a moment arm. The greater the wingspan, the greater the velocities near the wing tip, the greater the change in angle of attack, the greater the moment that poses the rotation. And finally, in the denominator is airspeed. The greater the airspeed, the less change in angle of attack due to rolling of the wings. Hence, the lower the moment due to roll damping. We'll defer further discussion on these aerodynamic topics to other lessons and simply point out that CLR is roll damping due to yaw rate. With our roll coefficient defined, we can go on to define the pitch and yaw moment coefficients. They have a similar form with damping coefficient, an angular rate, and a reference length in the numerator, and airspeed in the denominator. Here, the direct damping coefficients, for example, pitch moment due to pitch rate, are set to -1. The cross coefficients, for example, roll damping due to yaw rate, were set to 0. So this simplifies damping in each body direction to single terms. These values are chosen for code verification purposes only. They are much larger than the actual damping of a brick. Nevertheless, we can substitute the coefficients to obtain expressions for the dimensional roll, pitch, and yaw moments. These formulas will now be included in our Python code. Recapping our check case, we will apply the same initial conditions as check case 2, but now with the aerodynamic damping models included. Let's review the updates made to include the aerodynamic damping in our Python simulation. We're here in main program. To run this, we're going to change the vehicle model to the third check case for the brick. If I go to the vehicle model folder, into the brick folder, let's open up bricks.py. And there are two functions here. The second check case and one for the third check case. As I scroll through, you'll observe the parameters that define the vehicle model. Here's where we have the roll damping, pitch damping, and yaw damping as -1, their coefficients. And then all of the data is stored in a dictionary that's returned. In the flat earth equations, there are no aero forces in check case 3. So it makes sense that drag, side force, and lift are set to 0. Here's our external moments, and you can see we have new functions CL, CM, and CN. These aerodynamic buildups are specific to the brick. So rather than trying to create a buildup that is universal, we create a specific aerodynamic model for each vehicle. This is done by placing a folder called Aerodynamics that contains new functions that define the aerodynamic coefficients or the buildups for each specific vehicle. These are contained in scripts for pitch, roll, and yaw coefficients. Inside the scripts are functions CL, CM, and CN. When we compute those, we need to dimensionalize them by multiplying by dynamic pressure, reference area, and a reference length. Let's go into pitch coefficient. You can see we take in the required data, airspeed, reference wing chord, pitch rate, and the damping coefficient. We compute the pitch moment coefficient and return it. A similar thing is done for the roll and the yaw. Back in main, let's run check case 3. Upon comparing our results to the check cases, we see agreement as before. Small discrepancies between the U and V velocity in NED with known causes, and a dead-on match by inspection to the roll, pitch, and yaw rates, as well as the W velocity component and NED. The Euler angles are in similar agreement as well. This case is verified. And our FlightGear visualization. The rotation of the brick decays due to damping about halfway through the 30-second simulation. As it approaches this volcano, it is no longer rotating, but fixed in orientation with respect to the Earth. We've looked at 3 check case simulations comparing our results to the verified data, and we showed we got a match, but it wasn't that simple. For check case 2 in particular, there were significant discrepancies between our Python simulation and the verification data. It took hours of careful review and troubleshooting until key errors were found as the cause of the discrepancy. First, there was a sign error in the yaw rate state equation. Second, there was also a moment of inertia error in the yaw rate state equation. A trigonometric error in the east position equation was found. Also, a trig error in one of the direction cosine matrices was found. And finally, very tricky error. We had to resort to a higher order integration method because the first order forward Euler method that was originally used caused error to build up to the extent that it created differences with the verification data. A second order Adams-Bashforth method was used, and then finally a Runge-Kutta fourth order method was used to get verification data to match our sim. To learn more, consult Stevens and Lewis, our primary reference. The NASA verification study can be found online in 2 volumes. And to learn more about connecting your Python simulation to FlightGear, check out VD Engineering's channel. Access this lesson and more at learngnc.com. To all my Patreon subscribers who keep this content coming, thank you. If you want to support the channel and gain access to the codes used in this lesson, exclusive tutorials, and more, check out my Patreon page, Learn Guidance and Control. That's all for now. Good luck. We'll see you in the next lesson.